Right, so for the next question, you're going to have to use a bit of logarithms, specifically the natural logarithm. So I think a good idea is to quickly revise what you need to understand about logarithms. So let's do a very quick revision of that, and then I'll tell you what the natural logarithm is. So you should know, like this log term here, so like log of 10 or whatever. And you can have log in different bases, and you do something like this. Log of 7 of 49 would be 2. But there's another one that you'll want to use, and that is ln. That's somewhere here. That's ln. And ln is also logarithm, just in a specific base. So you don't have to use it. It is just convenient to use. So let's quickly revise logarithms and what you need to understand about it. Okay, so the basic idea is, if you have that, let's say, x to the power a is equal to b, then the power to which x has to be raised to get b is a. If you raise x to the power a, you get b. In other words, now in logarithm form, that you write it this way, which is the log xb, which you read as the power to which x has to be raised to get b is a. So for example, let's say 2 to the 7 is 128. Then the power to which 2 has to be raised to get 128 is 7. Right, so these are logarithms, and you should have seen a lot of these. Now, there are two important properties about logarithms that you have to understand. The first one is, the power to which a number has to be raised to get another number to the power something else is just 8 times the power to which x has to be raised to get just that number. So the power to which x has to be raised to get y to the power a is just 8 times the power to which x has to be raised to get y, which you can easily prove using your exponent laws. Okay, so if you have a logarithm expression with the power here, you can take the power out. That is what you've got to see from that mechanically. So that's the one important thing, that's the one important property. And the other very important property, which follows directly from, by definition, of a logarithm, is, let's say you've got, let's use base x. The power to which x has to be raised to get x to the power a is just trivially a, by definition, directly from the definition of the logarithm. What is this over here? That this is the power to which x has to be raised to get what? To get x to the power a. The answer is trivially a. So that's like saying, so for example, e.g., to what power would you have to raise 7 to get 49, right? So that it's the power to which 7 has to be raised to get 7 squared. To what power do you have to raise 7 to get 7 squared? Trivially 2. Okay, that's all that is. Okay, so these are the two important properties that you have to understand. Okay, now so a logarithm is relative to a base, which is what a button like this would be for. So if I wanted to write that, for example, I would say log 7 and 49 to get 2. Right. But how about if I just use log? What would that be? That's something else entirely. Okay, now what that is if your base is 10, then you often don't write. The actual base as 10. So if you just write log of some number, let's say z, then that is defined as just log base 10. The power to which 10 has to be raised to get z. Okay, so this is just a shorthand notation when the base is 10. Okay? Right, and there's another one. If you write ln, so that's an L, not an I, an L. ln of z, this is just a shorthand notation for when the base is e. Remember e, we talked about that. It's an incredibly important number in mathematics, arguably the most important noteworthy number. So there it is, the little e there, you'll see it. E to the power 1 is, that is a rational number, right? So you'll often see it in exponential form. That is where you would see, if I want to quickly draw it, what you'll often see is e to the x, which will look something like that, y equal to e to the x, so like a normal exponential function, right? You'd recognize the form, but that with the property that the slope here at the y-intercept is exactly 1. Okay, but that can be used, if you want, as a definition of e. It's that positive, that greater than 1 constant, such that it's exponential as slope of 1 at the y-intercept at x equal to 0. You can use that as definition if you want. It's not a historic definition, but that would be an equivalent definition. What is far more useful about this e to the x function is that if you differentiate it, you just get it back. This is not true for other exponential functions. It's specifically true for e to the x. If you have something else, if you have something like another exponential function a for some positive value a, then the answer is ln a to the x. That's general value. But if it's e, then it's e to the x and it's ln e, and ln e is just 1. Okay, but this is just some background about e. This e to the x. This e to the x is a ridiculously important function in mathematics, and it pops up just about everywhere. In particular, it pops up in these kind of RC circuits that we talked about, where you have formulas that describe the charge and the voltage over a capacitor as it is actually busy charging. And the expression for those are in e to the x terms. And we've got to use logarithms because of this property. Because the values that we would be after, the time values, would be stuck in the exponent, and to get to them we would use this property. Of course, we want to use the basis, so specifically what we'll do is we might have a value something like e to the it doesn't matter, 17x, for example, equal to pi, whatever. I'm just thinking about anything at this point. Now let's say you want this x. How can you get this x? Well, you rely on this property. You just take a logarithm on both sides. You don't have to take a ln, but if you take ln, it is the simplest. If you just take ln, so if you take ln on both sides, ln of e to the 17x is then equal to ln of pi, right? And this is, what is this? This is shorthand notation. This is the power to which e has to be raised to get e to the 17x, so this is just 17x. That's just using that property in terms of the shorthand notation. 17x, and this is equal to ln pi, so x is equal to ln pi over 17. Right, so that is why we'll be using ln. You don't have to use ln if you don't want to. I mean, you can also, if you really want to, you could just take a normal logarithm. Let's just use the normal base 10 one. That one will also work. And you can say log e to the 17x is equal to log of pi. And then you would again use this property, and the power 17x would come out. So you'd have 17x log e equal to log pi. So you would have that 17x is log pi over log e. But this actually is just by another property of logarithms. This is just ln of pi. If you can't remember what that is another property of logarithms, which is very useful. Very nice function, logarithm. What color? Blue? Yeah, fine. It's a logarithm, let's say two bases, x and y is equal to log of any base a y over log a x. Well, this is not important for our purposes, but that was just to explain why that is len e. Yeah, so you don't have to use len, but because we will have e functions, it is easier to do it this way than to do it that way. So this way still works if you know about this. Well, you don't even have to know about this. You can just calculate that directly. Log pi over log e. You can calculate that. Well, let me show you. I mean, so I claim that is len pi. So let's check if I remember correctly. So what is log pi divided by log e to the power 1? Good, and we get that funny value now. Can you remember it? Now let's see if that is equal to len of pi. It would be embarrassing if it isn't. It should be. Okay, and it is. Good. Okay, so it's fine to do it this way, but it is simpler to do it this way. Okay, so this covers everything you need to know. Well, more than you need to know. You don't need to know this or this or this. Just that if you've, this is essentially what you have to know. If you got an e function, well, it doesn't have to be an e function, but it will be an e function in your case, and what you're after is stuck in the exponent, then you take the natural logarithm len on both sides, and this just changes into 17x, all the exponent, and len pi, which you can easily calculate. Okay, so basically this is what we want to get to, how you can get to something stuck in the exponent. Okay, that's it.